Hey guys, so I just got my hands on the 2024 physics exam, so let's get started. Let's see how we go. Joe is standing inside a lift that is traveling vertically upwards at a constant speed of 2 meters per second as shown. Joe has a mass of 75 kilograms. Which one of the following is the closest to the force exerted on Joe by the lift floor? Okay, so if I were to redraw this, it's currently just this. Basically there is no upwards acceleration because the lift is traveling vertically upwards at a constant speed, which means no acceleration. So it would just be 9.81 times 75, which is, let me just put that in the calculator. 9.81, so that is 735.75 newtons. Closest to C, a space-based observatory SBO of mass m has a circular orbital radius r around the Earth. Modifications to the SBO have doubled its mass, but its orbital speed is kept constant. Which one of the following is the closest to the orbital radius of the SBO after the modifications have been made? Right, okay, so we can use this formula. So V is equals to Gm on R, which would imply that V square is equals to Gm on R. So our mass is going to be RV squared on G. Okay, so then V squared and G are basically constant, so our proportionality will go like this. Okay, so the key part is that it's the mass of the satellite that is changing, not the mass of the planet, because it's still revolving around Earth basically. So the big M actually doesn't change. So I feel like the radius still has to be R. I'm gonna go with B here, if that makes sense. So yeah, I'm gonna go with B. Okay, the diagram below shows a small ball traveling at a constant speed on a horizontal circular path while suspended from the ceiling by a string. Okay, which one of the following best represents the forces acting on the ball as seen from a front on view? Right, so one of them would be the tension, and the other one would be mg. Well, the tension has to be from the middle as well, just like that. Okay, yeah, that's pretty much about it. So just A for this. Okay, right. Moving on. A diagram below shows a 50-gram ball and a spring inside a horizontal launching tube. Assume that the launching tube is frictionless and the mass of the spring is negligible. Okay. Force versus compression graph for spring is drawn below. Consider the spring to be ideal. Okay. The spring is initially compressed by a distance of 10 centimeters. I'm just gonna underline that, with the ball in contact with the compressed spring. A short time later, the spring is released. Which one of the following is the closest to the speed of the ball as it leaves the tube? Right, okay, so this is like energy question basically. Okay, so let's write the equations down. So half mvi squared plus half k delta x I squared. Well, I don't need the delta if I'm just initial. So initial elongation squared. It has to be the same as half mvf squared plus half kxf squared. Okay, so this would simply just be 0, and this would simply be 0, because at the initial stage the ball is not moving, so kinetic energy is going to be 0. However, there will be some spring potential energy, And here there will be some kinetic energy, but there won't be any spring potential energy because just the ball is gonna be here, so the spring will have no elongation when it's like leaving the tube. So half ki squared is equals to half mvf squared. So then half and half will cancel out, so vf squared is equal to kxi squared on m. So vf is going to equals to kxi squared on m, the square root of course. So we have to find the value of k using this graph. So we can just use this these coordinates. So force is equals to k times delta x. So then k is equals to force over delta x. Okay, so then force is going to be 40 Newton divided by, this is in centimeters, be careful, so that would be 0.1 meter. So that would be 40 divided by 0.1, okay, 400, okay, so 400 newtons per meter. Okay, now we just simply substitute the values in here. So our VF is equals to the square root of 400 times the initial elongation, I believe it's 10 centimeters, yep. So 10 times 10 to the power of minus 2 squared divided by the mass. What is the mass again? 50 grams. So 50 times 10 to the power of minus 3. Let me plug that in. Let's see what we get. So square root of 400 times 10 to the power of minus 2 squared divided by 5. 50 times 10 to the power of minus 3. So that is giving me 8.944. So I'm going to go with option C, just here. Okay. So a rock is dropped from rest at the top of the cliff towards the ocean as shown below. Which one of the following graphs best represent the rock's total energy as it falls towards the ocean from top of the cliff? Ignore air resistance. Well, if there is no air resistance, if it's in an ideal condition, the total energy remains the same throughout. So it's just going to be option A for this. Okay, two magnets are placed as shown in the diagram below. The magnets are identical and point X is exactly halfway between two south poles. Which one of the following best describes the strength of the magnetic field at point X? Okay, so it's going to be looking something like this, basically. Like so, and same with this, like that. So option A for now seems quite good. It is half the magnetic field strength. No, twice. No, it's about the same magnetic field. No, okay, I think it's gonna be option A. The other ones are not quite there. Okay. So diagram A shows a single loop of a wire carrying a current I within a uniform magnetic field. Diagram B shows the same loop rotated clockwise through 90 degrees. Okay. The magnitude of the force F on side PQ and magnitude of the torque on the loop in the diagram B are compared to those in diagram A. Which one of the following rows in table below best describes the comparison? Okay, so we have to use our right hand for this. So using our right hand, we can see that the force actually doesn't quite change. So option B and C, we can rule them out. Now if you want to use our right hand, we point our fingers in the direction of the arrows. So you will notice that the current or the thumb is pointing at the front, so like just in front of you, and then our force would be going downwards. So at this point, let's say our force is going downwards like that, and this is our force. So then if you were to look at the distance like this, because remember torque is basically force times the perpendicular distance, essentially, right? So here, this is going to be the torque A, which is, I guess, pretty much the maximum. And in this case, the force is still pointing like that, I believe. However, the distance no more is perpendicular. So our torque A will be greater than torque B. So it's going to be option D for this one, I believe. Yeah. Okay, option D I think is the right one. Okay, a straight wire P, 4 centimeters long and carrying a current of this, is completely placed in a uniform magnetic field. This, okay, magnitude of this, okay. Which of the following is the closest to the magnitude of the force acting on the 4 centimeter long wire in the magnetic field? Okay, so for this, we can just use the formula F is equals to N times I times L times B. So our N is going to be 1 times the current, which is 5 amperes, times the length, what was it? 4 centimeters, so 4 times 10 to the power of minus 2, and times the magnetic field, so just 2 times 10 to the power of minus 3. Okay, let's plug that in the calculator. So 5 times 4 times 10 to the power of minus 2, not 3, times by 2 times 10 to the minus 3. Okay, scientific mode. There we go. So I get an answer of 4 times 10 to the power of minus 4 Newton. So option C. Okay. Two equal positive charges are separated by a distance d, exert a force F on each other. The distance is changed so that two charges now exert a force of 6F on each other. Which one of the following is closest to the new distance between the charges? Okay, so we'll use the formula F equals to K Q1 Q2. I mean, they are the same in this case. R squared. So all of this is pretty much just going to be constant. So F is inversely proportional to 1 on R squared. So for this, I just use a simple technique that I just make R squared the subject, because that's what we are kind of finding. So R squared is going to be the subject, is equals to 1 on F. Now, we are timesing the force by 6, right? So rather than F, I'm just going to say R squared is equals to 1 on 6, because we are timesing the force by 6. And now we just solve for the value of R, so 1 on 6, a square root of 1 on 6. Let's see what the calculator has to give us. So 1 on 6. So I get 0.408. Yeah, so it's going to be option B for this. Yeah, so I just use this kind of a thing to solve the proportionality problems, make things a lot more easier. Okay, moving on. Question 10. The graph below shows the induced current through a coil of conducting wire as a function of time. Okay. Which one of the following magnetic flux graph corresponds to the graph of the induced current shown above? Okay. So I is equals to V on R. Now I think R is going to be the same here. So just gonna remove that. So then E is basically going to be equals to change in flux, not theta, change in flux on time, right? So in that case, if you want flux, so equations of flux, we'll have to integrate this. So we'll have ET plus C, right? I mean, usually it's like negative, so this will be indeed negative, but I don't know, it's a bit weird, because none of the options are actually looking like there will be a negative involved here. Anyway, so now we have a equation to determine the flux when induced current is given. So like, let's say that this is our 1, this is 1 and this is 2, for example, right? Yeah, so our induced current will basically become T plus C or whatever that is. So we'll have like a graph would have something like this, and then here this portion, as you can see, if we integrate this, we'll have a higher gradient, the more steeper, and then we are back to the normal one, so it will have something like this. So I think, yeah, option C, there we go. So yeah, option C matches the graph. Yeah, okay. In Victoria, the electrical energy generated at the Loy Yang A power station is transmitted to Melbourne, approximately 170 kilometers away, using a 500 kilovolts transmission lines. Okay, which one of the following best describes the reason for the use of high voltage transmission of electrical energy over long distances? Transformers can be used to increase the voltage. Yeah, but that is not what the question is asking us. The question is asking us for the reason for the use of high voltage transmission line and not the transformers, although it's related. High voltage reduces energy loss in the transmission lines. Yup. High voltage can easily carry large power required by cities. Yes. High voltage can reduce the overall total resistance in the transmission line. So my understanding, so basically what we can do here, we know that power is equals to voltage times the current. So V is equals to P on I. Now because this is a high voltage transmission line, and we'll just assume ideal conditions, so that would mean that voltage is going to be inversely proportional to current, or not resistance, current. There we go, right? And now our formula for power loss is also I squared R. So that means the more voltage we have, the better it is, because then there is less power loss basically. So the answer is going to be reduced energy losses, essentially is the correct choice here. I hope that made sense. Yeah. Okay, so I just forgot to explain one part. Why is the power constant basically? So the reason being that, so these lines usually actually use transformers, and we can assume that the transformer is ideal. Transformer is an ideal transformer. We can assume that for this question. And so then there is actually basically no power loss if the transformer is ideal, right? So that's why power is constant here, and that's why we get this proportionality basically. That's how we get it. So hopefully this makes a bit more sense as to why power is considered constant here. But yeah, okay. The diagram below shows a coil moving upwards from the north pole of a stationary bar magnet. Alright, which one of the following correctly defines both the direction of the induced current as observed from top of the coil and the direction of the magnetic field produced by the induced current inside the coil as observed from the side of the coil? Okay, so basically this object is slowly going away like this, essentially is the gist. Now when it is closer to the magnets, that means more magnetic field lines are passing through it, right? Now if we were to move this away like this, so now currently there will be less magnetic field lines, so like this and like that, and then like that. I mean, they should not touch, but anyway, I'm just explaining, right? So that means there is a reduce in the magnetic field. So magnetic field is currently reduced like that, and because using the Lenz's law, because the Lenz's law states that we have to oppose it, it's gonna be in this direction. So now if I were to point the thumb going up like that, we can see our fingers curl in the anti-clockwise basically. So our answer here is going to be option C. Hopefully that made sense. So it's just all about Lenz's law, that because magnetic field is going this way, to oppose it, it has to go the other way. And then now if I were to point my thumb in the direction of the opposing magnetic field, we can get the current direction of the induced current. Basically we can get the induced current direction. Okay, hopefully that made sense. So moving on to the question number 13. The diagram below shows a simple generator made from a loop of wire, a commutator, and magnets. A mechanical energy source rotates the loop smoothly. The magnetic field is constant and uniform. The output is displayed on an oscilloscope. Okay, which one of the following best describes the output that it will be observed by the oscilloscope? It would just be A, DC voltage with a varying value. Yeah. Okay. A rocket passes a space station at a horizontal speed of this parallel to the side of the space station. Okay. There is a circular window on the space station as shown in the diagram below. Alright. A person sitting inside the rocket observes and measures the window of the space station. Which one of the following statements best describes the measurements taken of the window of this space station? Okay. So it would basically just become like this because we are going at a very, very high speed. It will basically appear that it's the width is less, basically, is the gist of it. So let's see which options actually match that. So both vertical and horizontal measurements will be less than the actual window. No. So the vertical measurements will remain constant. It's just the horizontal one. Okay. So option A is ruled out. Will be the same as the actual window. No. The horizontal measurement will be the same as the actual window. Incorrect. That's the one actually changing. The horizontal measurement will be less than the actual window. That's correct. But the vertical measurement will be the same as the actual window. Yes. So it's going to be option D for this. At the Australian synchrotron, electrons are accelerated to close to the speed of light. C. By linear accelerator. Consider the electrons that enter the Australian synchrotron booster with a Lorentz factor of this, and as a result of further acceleration in the ring, reach much higher value with a Lorentz factor of this. Which one of the following best describes the effect of a booster on the ring on each electron speed and energy? Okay, I guess, so what we can do for this, okay, interesting question by the way. So this is our Lorentz factor and this is our velocity. So using the relativistic model, our graph would look something like this. Well, no, not quite, like that, basically, where this is our speed of light. Okay, now if we see that if we are very close to the speed of light, so like let's say we are somewhere around in this sector, okay? Now if I increase my Lorentz factor from 200, which is let's say here somewhere, well 200 somewhere here and 2000 somewhere here, I know the scaling is very off, but just imagine there will be, okay, what is this question? Okay, the electron speed increases by a large amount and energy increases by a large amount. Okay, the electron speed increases by a small amount, energy increases by a large amount. Okay, the electron speed increases by a large amount, energy increases by a small amount. Right, the electron speed increases by a small amount, energy increases by a small amount. Okay, I'm not 100% sure with this question, so if I do get it wrong, just let me know that in the comments, and yeah, let me know actually like what the actual answer is. So as we approach like the speed of light, like I was saying before, we see that regardless of how much we increase the Lorentz factor, the change in the actual speed is going to be quite minimal as we approach like to the speed of light, basically. So I'm going to say that the change in speed is going to be lower, and in regards to the energy, so energy will be gamma times mc squared. So as you can see here, there will be like a solid 10 times increase basically. So I'm going to say that speed increases in a minimal amount and energy goes up by a bit. So that's what my answer is gonna be. I think I'm gonna go with B for this, but I'm not entirely sure. So if I'm wrong, just let me know. Thank you. Diagram P below shows 5 energy levels of an atom with 5 transitions indicated. Diagram Q shows 4 possible sets of spectral frequency lines. Okay. Which one of the following frequency spectra shown in diagram Q best corresponds to the transition shown in diagram P? Sorry. Right, so for this, the first 3 here are going to be high frequency because we can see that they're like the drops are significant. So I'm going to say that the first 3 is going to be high frequency. So it could be option, well, definitely not option A. Option B, maybe. Actually, can't be option B as well because this one would be a bit lower. Okay, can't be option C either because there's only 2, but we need 3, so can't be C. And option D has 3 and okay. Like the gap between these two is quite big, I would say. I don't think it's gonna be option B. I'm gonna go with option D for this, like the spectrum D. So yeah, because this tree has spacing, like correct spacing of the drops, like they correspond to the drops, which is good, and that is high frequency, which is also good. And these two also have good amount of spacing between these two here. So I'm gonna go with option D. Option D seems like the safest one here. Okay. The diagram below shows a standing wave on the stretch string between 2 fixed ends at time t equals to 0. The frequency of vibration of the string is 50 Hz. Which one of the following diagram correctly shows the position of the string at time t equals to this? Okay, can't be option D, can't be option C. That just... yeah, I don't think it's gonna be that. Because the ends are fixed, so they can't move. So that's why it can't be option D. And actually, it could be option C. Let's calculate the period first. So our frequency is equals to 1 on t. So that means our t is going to be 1 on frequency. So 1 on 50. That is going to give us, let me see, 0.0, wait, 1 on 50. Yeah, okay, I was right. So 0.02. I'm just going to check. Okay. It can't be option A because it doesn't ask, yeah, it's asking at this point. So I don't think it's option A for this. And I don't think it's going to be option C either. Just going to go with option B for this. Yeah, because I mean, this would come down like that. So I think that would make most sense. I'm going to go with option B for this. I don't think it's going to be option C either. So yeah, option B sounds the best. Okay, question number 18. An interference pattern is produced by monochromatic light, is viewed on a screen placed at a distance L from a double slit system with slit separation D. The distance between the centers of 2 adjacent bright bands is delta X, okay? And the distance L is doubled and the slit separation D is halved. Which one of the following is closest to the new distance between the centers of the 2 adjacent bright bands? Okay, well, so this is again just the proportionality based question. So delta X is equals to lambda L on D. Okay, so lambda just stays constant, I guess, and delta X is equals to L on D. So distance is double, so we'll put 2, and D is half, so we'll put 0.5, and that should give us 4 basically. So 4 delta x is the correct one. Okay, hopefully that makes sense. Alright, question number 19. The orbital velocity of a satellite in an orbital radius r around a planet M is given by this. Which one of the following linear graphs is consistent with this relationship? Okay, well, it's just gonna be D, pretty much. Yeah, because if we square it, we'll get v square, and yeah, gm is just constant. Yeah, so yeah, D makes most sense. Okay. Yeah. Alright. Data can be described as precise when it is the result of a careful investigation. No. The experiment is repeated many times and the results show little variation. Yes. Option B. Okay, so I guess, yeah, this is it for section A for Physics 2024. Hopefully you guys did alright. Now, if I did anything wrong or made a mistake, just let me know down in the comments. I'm happy to rectify it. Thank you for watching, and I will hopefully do the extended response soon. See you in the next video. Bye bye.